Very simple. Okay. So at the same time, I will try to give more details about the main property used in quantum algorithms, which is entanglement. This is a kind of weird property, and it is I think it is anyway good to have about. So back again to our map. So we were around here in the first lecture. Now we move to the top of the map and review the basic concepts of quantum mechanics. And once again, to start with like a game, not to make the lecture too much annoying for you, this is one of the most iconic pictures in the history of science.
And there is only one woman, huh?
Yes, yes.
Can you show us?
You have a good eye, Malik. Yes, this will be one of my questions. So, Solvay 5th conference, 1927. Okay, with, as you can see, a very distinguished panel of physicists, and the game will be the following: how many of them you are able to recognize? It is a good opportunity to pay tribute and to acknowledge the contribution of these brilliant guys what we are having today. So it is good to try to guess who they are, or at least part of them. This one is quite well known.
The famous one.
This one? This is Einstein, of course. And Malik, yeah, Malik already mentioned Marie Curie, the only woman
Who has had 2 Nobel Prizes.
Exactly. So she is the only woman, but she is also the only scientist who had 2 Nobel Prizes in 2 different scientific disciplines. She's the only one. In physics and in chemistry. So any guess?
Max Planck nearby Marie Curie.
Yes, this is Max Planck, exactly.
Near Bonn.
Where is Bonn?
Near Einstein.
Near Einstein.
No, Langevin, nearby on the left side of Albert Einstein is Langevin. Correct?
Yes. So the very famous people like Schrödinger, Heisenberg were young at that period. So this is this may help you recognize them. They are very young. They were. They are all dead now. Okay.
The art in between Einstein and
You have the answer.
Thank you for that.
So you have the names here, and the main players in the game here are, of course, Einstein, of course, Bohr, Heisenberg, Schrödinger, Wolfgang Pauli, Louis de Broglie, Max Born, and the grandfather of quantum mechanics is Max Planck, as you know. And there are other brilliant physicists as well, Brillouin, Ehrenfest, Bragg, and many, many others. Okay?
and hopefully maybe in the future we have a really geometrical plane for that.
So these are the main points when you speak about the concepts of quantum mechanics. The first one is the wave-particle duality. Malik is playing with that all the day with the neutrons and showing very nice wave properties of neutrons, making neutron optics and so on. Superposition of states, the time evolution of quantum state, the measurement, and the entanglement between two quantum systems. These are the main points. In blue are the two most important properties for quantum computing: superposition and entanglement. We will see in detail what it means exactly and how to use it. Well, a quantum system is in general a system with quantized energies. Everyone knows that. And to make it simple, I will consider as an example to illustrate all these concepts a two-level system. A two-level system is simple with only two levels, level 1, level 2, two different energies, ground state and excited state. Okay. Why that? Not only because of its simplicity, but also because this is the basic model for a qubit. A quantum bit is a two-level system with two levels, ground and excited, which will be labeled later on 0 and 1. Okay. So before that, just to say a few words about the wave-particle duality of quantum particles at the atomic level. Let me here mention a quite recent work published a couple of years ago. It's a kind of double-slit experiment showing, as you can see here, a modulation, which is the signature of fringes, like bright and dark fringes, with what? With molecules, but not any molecules, very big molecules having like 2,000 atoms. So in the very beginning of quantum mechanics development, people were able to show interference between particles like electrons, Davison and Germer, very old, then with protons, neutrons, for a long time now, and still in use, but later with more heavy systems like atoms, atom interferometry, then with small molecules, and now with bigger and bigger systems. So even with these huge molecules with more than 2,000 atoms each. So this wave property is maintained even in such big systems, and in the paper you can read that it will be possible in the future to demonstrate wave properties of systems which are even larger than that, maybe one day even viruses, which are at the end of the day kind of very big macrobiological molecule. Okay? So you have the reference here if you are interested. It's a group in Vienna, Marcus Arndt, and it is in Nature 2019. So the point here is just to say that wave-particle duality is something very, very well established, and it is the everyday life in quantum labs. Superposition. So what is superposition? If you take a classical system, like a coin, I don't know if I have coin. Yes, I do. A coin here, it has two sides, of course, tail and, how to call it in English, and heads, tail and head. And a coin, if it falls down, it will be in one or the other state. And it is exclusive. If it is head, it cannot be tail, and if it is tail, it cannot be head. It is binary, 0 or 1, black or white, red or blue, tail or head. Okay, only two possibilities. For physical systems, it can be like a capacitor, for instance, charged or discharged, and many other examples. However, and this is one of the weird properties of quantum systems at the atomic and subatomic level. If you have a quantum systems with two levels, the system, we can denote them, for instance, 0 and 1 with this specific notation. This is called the ket. The ket, this is a Dirac notation, but whatever, doesn't matter here. It's like a vector. You can see it like a vector, okay? If you know about vector space and some geometry, it's exactly more or less like a vector. So if we denote them 0 and 1, the system can be in state 0. This is one possibility. The same system can be in state 1. This is the second possibility. But the system can be also in any linear combination of both states. So any linear combination with the scalars alpha and beta, which are just numbers, of state 0 and state 1, of course with a kind of normalization condition, the norm should be always saved. This is a state, psi is possible. And you see that there is an infinity of possibilities. And this is what is called superposition. And it is not very, it can be like counterintuitive for us, because in our everyday life, we cannot have at the same time a system in both or a combination of states. I cannot be here and there at the same time. But an electron can be, or to be more specific, it can be accurately described by a wave function, saying that he has some probability to be here and some probability to be there, being like ubiquitous. Okay. And by the way, when these notions were introduced in the early 20s of last century, of course, it was not easy to understand and to accept. And people, very brilliant physicists like Schrödinger, was very embarrassed by that. Einstein too, saying it is not possible. We cannot have this ubiquity. A very famous and shocking example cited by Schrödinger to say that it is not possible that the matter behaves like that. Is what is called the Schrödinger cat paradox. Do you know about Schrödinger cat? Who already knows about Schrödinger's cat? Who never heard about Schrödinger cat? Don't be shy, it is an opportunity to do so. Yeah, thank you. So the question raised by Schrödinger is the following. If the ideas of quantum mechanics are true, and if they apply at the world at our macro human level. So follow me and imagine this experiment. I have a cat, an animal, living animal. I put it in a box, a closed box, with a bottle containing some poison that can be broken by a hammer, and the hammer is controlled by radioactive source. As you know, you are here in the nuclear center. It is governed by probabilities and statistics of the stochastic phenomenon. So you do not know, you know that with some probability a particle will be emitted, but you never know when exactly. It is probabilistic. So the idea is the following. You close the box. You have the following information: the lifetime of the particle, let's say 1 hour. So you have some probability that the particle is emitted at 30 minutes. And if you wait 30 minutes, the question is the following: is the cat alive or dead? Isn't it? It may be alive or dead, depending on what you cannot see, if the particle was emitted or not. And then Schrödinger say, so how should I describe my cat? Can it be in kind of superposition of half live and half dead? This is shocking. And the idea was, okay, so this kind of probabilistic description of the world cannot be the good one. And this is the beginning of one interpretation of quantum mechanics, not that the Göttingen school, led by Schrödinger, but first by Einstein, who are saying it is not possible that the world be probabilistic. There should be some kind of deterministic rules, and I will go back to this debate later. But this is the main idea. So once again here, the same picture, just to mention this debate between the two schools, and Einstein, leading this school, was saying to Niels Bohr, the other school, the probabilistic one. You know this citation, yes? God does not play dice. What does it mean? It means that the nature cannot be governed by probability. There should be a kind of much more deep level theory explaining the world. To this, Bohr replied in the same register, very brilliant answer. You can read it. Einstein, stop telling God what to do. This is really brilliant. This means that actually we do not know how God is governing the world. So don't say it should be like that or it should be like that. Just say, I understand, I think it should be like that, or I think it should be like that. Okay, very, very brilliant. Now to, especially for people who are not familiar with the quantum, to give you a flavor what superposition can be. Courtesy to our friends at APS. So please answer the following question. How many cubes do you see in this kind of 3D kind of optical illusion? 10? So Malik, you say 10. Okay, any other guess?
According to the red faces.
Maybe if the boss says 10, everyone, you close the debate.
No.
Guess 66.
All you need is just to look and count. No, I don't think so. Maybe, but you see 10 as well. Okay. Hmm? 16. Why 16?
Looking from the top.
Okay, but maybe you can reformulate the answer in another way. It can be 10 or 6 at the same time. You see the point? Is anyone seeing 6 cubes? Hamza. 6. Actually, it depends. If you see this, as the top of a cube, of this cube, you will see 1, 2, 3, 4, 5, 6. But if you see it at the bottom of this cube, as Malik did, you will see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you can see 10 or 6 depending on how you did the measurement. What does it mean? It means that there are 2 possible answers actually. And no one of the 2 answers is false. There are 2 possibilities. And this is a kind of simulation of 2 state level with 2 values. And the number is decided when you make the measurement, when you accommodate your eye or your vision. I mean, when you see 10, you cannot see 6 anymore. Or when you see 6, you cannot see 10 anymore. And what you mean by 16 is the sum of both. Okay. So before doing the measurement, a good description could be that it is a kind of superposition if the quantity is the number of cubes, it is superposition between 10 and 6, some combination, and when you make the measurement, it is 10 or 6. Of course, this has nothing to do with real quantum, but just to illustrate it. So what you can imagine better is a real system, like an atom with 2 levels, or a superconductor, or something like that, and consider the possibility that the state or the system can be in a state which is a superposition of both. Okay. So then I need, of course, some basic knowledge in quantum mechanics, just to remind that the system, quantum system evolves according to the Schrödinger equation you are talking about, the type-dependent Schrödinger equation, the type evolution. This is a postulate. And this evolution can be described by an evolution operator, which acts on the state of the system at some initial time, t0, to give you the state, the description of the state at any time t. And this is how we illustrate in quantum mechanics the two systems, level 1, level 2, and you can have either absorption or emission of photons, as you certainly have seen somewhere in like Bohr model or very basic quantum mechanics, even in the very early years of studies at the university. Okay, so I skip this at the second part. Now the measurement. So what I'm doing here is reviewing the postulates of quantum mechanics. It's not very easy when you never did quantum mechanics before. But let me say it in a different way. Okay, I will not use exactly what is in the slide, but try to explain it differently. You have a two-level system with two energies, and you measure the energy of the system. So what are the possibilities? As we said, if you make the analogy with the number of cubes, it can be 10 or 6. It cannot be 8, it cannot be 9, it cannot be 12. It is very precise. It can be only 10 or 6. These are called kind of eigenvalues. When it is when we are dealing with the energy, for instance, of an atom, it can be the energy of the ground state or the energy of the excited state, and nothing else. Okay? So the only possible values you can get are these two called eigenvalues. Some algebra they can be put in as diagonal values of some operator. Okay? Now the question is, as we said, that you have some probability. What would be the probability to get this one or this one? Is it always 50%, 50%? The answer is no. It depends on the state. So if the state has a larger component of the ground state, the probability to obtain the ground energy is higher. It makes sense, doesn't it? Yes. So in general, you have the probability to obtain a given value depends on the state you are dealing with. Okay. The second point, also to make the analogy with the cubes, I said before we say accommodation for the accommodation. What to say in English? Focus. Thank you very much. Before focusing your eyes on the in some way and to see either 10 or 6, you do not now know how many cubes there are. But after doing that, if at some time you see 10, it is 10 and it cannot be 6. It's exclusive. In terms of quantum states, it is called the collapse of the wave packet, which means then before the measurement, it can be the ground or the excited. But if you do the measurement and you find the ground state, even if the wave function before the measurement was a combination, this is no more the case after the measurement. It should be the ground state, if you find the ground energy, or the excited state, if you find the excited energy. This is the collapse of the wave packet, which is a bit mysterious, actually. But, well, this is quantum mechanics. Okay. So now, the qubit. What is a qubit? The qubit is a two-level system. Is this idea clear enough? Simply a two-level system with states labeled 0 and 1. Real examples can be two levels of an atom. You know that atoms have discrete levels. You can choose a couple of them, the ground state and excited state. Or if you take a 1/2 spin particle like an electron and put it in a magnetic field, you know that you have two possible states, spin up or spin down. These are the main examples, and you have also others. And the notations can be 0, 1, ground excited, plus and minus, up and down, or any other combination of two possibilities. You can use also colors or whatever. So I hope you see it's more clear now that a state is a combination of both, and alpha and beta are scalars that verify the normalization condition here. The algebra behind this is very simple. It's like the vectors in a plane. Vector 1 and vector 2, they are orthogonal and they are normalized. So this represents the scalar, the inner product, scalar product. So this is the norm, should be 1, and the inner product is 0 between two orthogonal vectors. Everyone knows what orthogonality means. Okay. A very convenient way to represent geometrically these states is to use what is called the Bloch sphere. What is the Bloch sphere? Alpha and beta, which are complex numbers in general, can be written like this, using the angles theta and phi in a very general way. And using this form is very useful because the angle theta and the angle phi are nothing else but the well-known angles and spherical representation of any vector in space on a sphere. Okay. So this is the Bloch sphere. This is the way the states are represented. The state 0, the ground state, is on the North Pole, if I use some geographic references. 1 is on the South Pole. And the state psi can be any combination of them all around this sphere, depending on the angles theta and phi. So when I say that for a classical system there are only two possibilities, this point or this point, tail or head, okay, so this can be tail or head. Any other possibility is excluded for classical system. A quantum system can be in a state which is any combination, so represented by any point on this unitary sphere. And this Bloch sphere is very useful to follow the evolution of the state, which can rotate from south to north, from north to south, from the equator here, etc. Okay. With some technical differences, I may skip them here. Yes. Yes. So this is how to describe a state. The state of the system is described by a combination of the two states 0 and 1. Now, how to operate on this system, how to change its state. Any physical change in the state of the system will be described by what we call a unitary transformation. Unitary transformation is something very simple, actually. It's described by 2 by 2 matrix. unitary 2 by 2 matrix. Does everyone here know about matrix algebra? Okay, it's very simple. No, not the big ones, only 2 by 2. And the U dagger is exactly the inverse of U. This is what is the unitary. And a simple example of unitary transformation, as I'm making the analogy with the vectors in a plane, is rotation. When you rotate a vector, it is a unitary transformation. It preserves the norm, so the length of the vector does not change, and also it preserves the inner product. So if two vectors are orthogonals, if you rotate them, they remain orthogonal. Okay? So the evolution operator is one good example of unitary transformations. There is a set of specific matrices which are very useful in quantum computing. These are called the Pauli matrices. What are the Pauli matrices? I said we will deal all the time here with matrices like this one. 2 by 2, very simple. These three matrices, called sigma x, sigma y, and sigma z, are known as the Pauli matrices. They are directly related to the spin of the particle. Okay, so you can see that they have a very simple form: 0, 1, 1, 0 for sigma x, 0 I minus I 0 for sigma y. I here is the complex number. I squared equals minus 1. It's the root of minus 1. And sigma z is 1, 0, 0, minus 1. Why these matrices are important? First of all, if you take any matrix M which is Hermitian, which means that it's equivalent to a dagger. If it is a real matrix, it means it's simply symmetric. You can always write this matrix as a combination of the Pauli matrices and the identity. So in some way, identity plus these three Pauli matrices form like a basis for all the possible matrices. Okay, so this is the first point. They have some mathematical properties. I'm not going to detail them, but you can just to check two of them, determinant and the trace. You can see easily that always the trace is 0, 0 plus 0, 0 plus 0, 1 plus minus 1, and the determinant you can easily check that that it is minus 1. Okay. So schematically, this is a qubit. Okay, this qubit two-level system described by a state psi, which can be a combination of state 0 and state 1, and you apply an operator on it that can change the state. So how to use this as a basic element in computing, especially if you compare it with classical bits. So what is done is the following. You prepare the qubit. Let's take here an example of 3 qubits, or even 1 is enough. You prepare it in some state, 0 or 1. The state evolves. At some moment, you make a measurement. And when you make a measurement, you can find either 0 or 1. And at that time, this is the value you get at the end of the day. So I would like to spend the remaining few minutes on this very important property, which is entanglement. What means entanglement in the context of quantum mechanics? First of all, when speaking about entanglement, we are considering a system with more than one part. So entanglement does not make sense for one particle by itself. A particle is entangled with one or more than one other particles. And we will keep all the time the simple example of 2 particles, say 2 electrons, for instance. or two atoms or whatever. Okay? What means entanglement? So let's take the example of two electrons. Each one, electron 1, can be represented by a state, like, let's say, up like this, or down. Okay? Up or down. And this one also can be represented by a state up or down. So if I consider the system of the two electrons together, what are the possibilities? You have two possibilities here and two possibilities here. So you end up with how many? 4 possibilities. Up, 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 down, down, up, down, down. Okay? Or if you use the more convenient notation of zeros and ones for computing, if up is 0 and down is 1, it will be 0, 0, 0, 1, 1, 0, 1, 1. Okay? So these are the 4 possibilities, 0, 0 for A and B, the two parts. And this symbol is what is called a tensor product. It means simply that the two particles are independent. So we have 0, 0, 0, 1, 1, 0, and 1, 1. Okay? So this is the basis. Like for a simple particle, we have only basis of 2 states, 2 possible states, 0 and 1. Now we are dealing with a system of 2 particles. So the dimension of the space is 4, 2 by 2, and the basis is formed by these 4 vectors. So as we said, for what was valid for one particle is still valid for the new system, which means that any combination of these 4 states is a possible state of the system. Any combination of these states is a possible value of, or a possible state for the system. Which means that, of course, the system can be in state 0, 0, 0, 1, 1, 0, or 1, 1. These are 4 possibilities. But you have, in addition to that, an infinity of other possibilities, which are combinations, linear combinations of these 4 situations. Okay? For some of these states, possible states, they can be factorized as a product of state of particle A and particle B. For instance, all these states can be factorized. This one, this means that you can clearly identify the state of each particle independently of the other one. Okay? However, if you consider a state like this, which is possible according to quantum mechanics, the state is 0, 1 plus 1, 0, a combination, a normalized combination. So you have to have here a normalization factor, which is 1 over square root of 2. The question now is, can you separate this state? Can you write it as the product of state of particle A by the state of particle B? So as you can see here, it is not possible. Why? Because at left here you have 0, but here you have 1, and at right you have here 1, and here you have 0. So you cannot, if you had 0 here, for instance, you can put 0A outside the brackets here and factorize the state. So what is what is the meaning of a state like that? This is what is called an entangled state, that means that the state of the whole system formed by the 2 particles is well defined through this state, but you cannot define separately the state of each particle alone. Okay? So the state of the whole is well defined, but not the state of each part. This is what is called entanglement. Mathematical derivation that of the existence of non-separable states. You can skip it. It is too mathematical, etc. I don't want to make this lecture too annoying for you, but you will have the material. You can review it later. So I skip this. Okay. And let me go back to the space of ideas and concepts, because you have the following problem to address actually. If imagine that you were able to form a pair of particles in an entangled state. Once again, what this means is that the state of the whole system is well defined, so it has some properties well described by quantum mechanics, but you cannot have the same for each part alone. So you take this couple of particles and you separate them even to very high, very large distance. The prediction of quantum mechanics is the following. If you make a measurement on the subsystem A and find some result, you immediately know the result of the measurement on the other particle, even if you do not realize it. You understand that? So imagine that I start by forming a pair of particles here at a temperature, and I send one of the particles to the other part of the galaxy, okay, to spin half particles. And an entangled state, let's say this one. This state. And this represents the spin up, spin down, spin down, spin up. What quantum mechanics say is if you separate the particles, if I measure the spin of particle A, there are two possibilities. I find 0 or 1. There are no other possibility. In this state, if A is in state 0, B is certainly in state 1. And if A is in state 1, B is certainly in state 0. So if I make the measurement for A and I find 0 here, I can say with 100% confidence that the state of the other particle on the other side of the universe is spin 1. Spin up or the value 1. But you can say, okay, what is the problem with that? The problem is the following, is that according to the very well established and assumed theory of relativity of Einstein, no information or matter can travel through space at a speed higher than c. Okay? And c at our scale is very large, 300,000 kilometers per second, but at the scale of the universe, it's very, very, very slow. So how to accept the idea that I can have an information on the other particle, for instance, knowing what spin state it has, while it should take millions of years, according to the relativity theory, to reach me. So it's a kind of paradox. You see the point? So this is what is called the EPR paradox, as raised by Einstein and Podolsky and Rosen in 1937. You can make the analogy with the Schrödinger. It's always the same school, saying that something is not good with the quantum mechanics. Okay? And of course, this paradox was discussed for a long time with between the two schools, between Einstein and Schrödinger and others, the Göttingen school, and from the other side, Bohr, Heisenberg, Max Born, and their colleagues. And actually, the question stayed over for a long time, even after the death of Einstein and Bohr. They both died before getting the answer. But the good news was that today we know what the answer is. This is the good news. Do you know what the answer is? Who is right? Einstein or, let's say, Bohr? Do you have an idea? Okay, you will get the answer now. Before that, an important step was achieved by John Bell in the 60s of the last century, who succeeded to imagine a kind of experiment, tabletop experiment, which can discriminate between the two theories. So depending on the results of the experiment, you can clearly say if entanglement is something that exists, and if quantum mechanics is the good description of the behavior of the matter at the atomic scale, or not, or if the quantum theory is missing something which is called by Einstein and his collaborators, like the local realism, and that the quantum mechanics has something called hidden variables. So whatever are the symbols here, just to get the point that there is some inequality, Bell inequality. If you remember the very first slide this morning about the Nobel Prize, the Bell inequality. So if Bell inequality is verified, Einstein is right. If Bell inequality is violated, Einstein is wrong and Bohr is right. Okay? So these are the papers. I'm putting them here because you can see here in the reference, the old-fashioned papers, not very long. The citations, here a citation by Einstein, who says very clearly, but on one supposition, this is Einstein speaking, okay? But on one supposition, we should, in my opinion, absolutely hold fast. Reference 2 for people following remotely. The real factual situation of system S2, S1 and S2, what I call A and B. S2 is independent of what is done with the system S1, which is especially separated from the former. So for Einstein, it is impossible that the measurement for the first system gives immediately and instantaneously information on the second. This is the point of view of Einstein. So at the same time, the conclusion of the paper of the work of John Bell is the following: if a hidden variable theory, this is Einstein theory, is local. Locality means this. The measurement on one system here cannot affect the state of a measurement which is very far from it. This is the local realism. So if the Einstein theory is local, it will not agree with quantum mechanics. And if it agrees with quantum mechanics, it will not be local. So then other people contributed, including John Clauser here, one of the Nobel Prize awardees of last year, making the formalism more clear. This is one of their papers in the late 60s. More important is the experiment of Alan Aspect, who did the experiment. So what he did, he took a source of untangled photons. It's a source of, actually you have calcium atoms can decay, emitting two untangled photons in opposite directions with two different wavelengths or two different colors. That can be detected on both sides, and their polarization, you know what polarization is, of an electric field or a photon, can be measured, and the equivalent of states 0 and 1, or spin up and spin down when dealing with photons, is regarding the polarizations in horizontal or vertical polarization. Okay? So the equivalent of the state we have seen before, 0, 1 plus 1, 0, should be HB plus BH. Here, ASP is using a different kind of Bell state, but it is also non-separable state. It is an untangled state. You cannot factorize it as the product of one state of the polarization by one other state. So here again, when you measure the polarization of the photon, if the couple of photons, if the measurement of the first photon gives you H, standing for horizontal, the only possibility for the other is H, because if the photon the first photon has a vertical polarization, the second one will have a vertical polarization as well.
Dr. Lee, would you please let me just to understand what, if I have understood, the source gives me two photons which are identical, and we split them.
They are not identical.
Sorry.
Yeah. They are not identical. They are formed in a state which is untangled and described by this state psi, which means also that we cannot speak about them individually to say they are identical or not. So once again, the state of the both photons is well identified, but not the state of each one. Yes.
And okay, thank you so much. And they are emitted at the same time, if I understood.
Yes.
And if I change the polarization one, then automatically the polarization of the other one will change.
This is the game. This is what Aspin wanted to check. So this hypothesis of entanglement, which means how does it work regarding the Bell's inequalities. So this is the point. By detecting both photons simultaneously in both directions. Okay. So this is the paper, and we, after some calculations, I'm not sure I will go into details here because it's a bit late. We show you the main point, and we can come back to the details later. Okay. So once again, what are we checking? Yes. You make the measurement and you end up with some quantity S, okay? S, which is given by this expression, depending on the both measurements on photon 1 and photon 2, if you are using photons. So the Bell inequality is that S is limited by -2 from one side and the +2 from the other side. This is what the theory gives. So now, the experiment is the following. You measure, you make your measurement, you extract S, and you check if it can be or not outside this interval. If by any chance S falls outside the interval, this would mean that the Bell inequalities are violated. This is the point. So with some specific apparatus here, varying the angle alpha between both polarizers. This is the experimental result obtained first. This is from the paper of Aspe. You can see that by varying the angle, the relative angle between the two polarizers, for some values, you can clearly see that the points are above 2 or below -2 for this specific angle, especially here at the maximum or at the minimum here, which corresponds to 22.5 degrees pi over 8. Okay, so this is the experimental value, 2.697 with this uncertainty, which is clearly by several sigmas, several tens of sigmas, larger than 2. And this was the first demonstration or proof of the violation of the Bell inequality. And this was just to make the link with the very first slide about the Nobel Prize. This is why Alain Aspect won the Nobel Prize of Physics this year. So also the other awardee was one of the team. Some of them died, and the rule for Nobel Prize it is never given post-mortem. And there is another limitation, only 3. So Closer got it as well. Okay. To finish this part, just to say that since this is quite old experiment now, in the 80s, later on several other experiments, more sophisticated, tried to improve the result, and the debate now is closed, especially after this work in 1915 by the people from in Geneva. So because on the tabletop experiment of Alain Aspect, the distance between the two polarizers was like 6 meters multiplied by 2, so few meters. Then more sophisticated experiment using fibers, optical fibers, over distances more than 1 kilometer, has given a value of S, as you can see here, 2.42 plus or minus 0.2, which is clearly above the limit of 2 and the proof of violation. Okay, so just to finish that, it's good to say that this experiment of Alain Aspect and other more refined experiments, what you call loophole freeze, because there was a debate if in the experiment there was something missing, or if there are loopholes that can be closed, etc. And finally, the debate was settled in favor of the probabilistic non-local interpretation of quantum mechanics, the Copenhagen school, Bohr and collaborators, to the detriment of deterministic interpretation. So to say it in a shocking manner, Einstein was wrong. It shocked some people because Einstein is not such a huge scientist, but he did a lot, he did enormous work in almost all the modern physics fields, but in some specific problems, his point of view was not the good one. But he, what is, of course, we are speaking of Einstein, you have to be very, very modest. Einstein was the guy who always asked the good questions, and this is very, very important. So now this property of entanglement is not only well proved, but also used technology. And for instance, you can see here this paper from Nature of 2020, an experiment by Chinese using a source of entangled photon, not on tabletop experiment, but on a satellite, and not sending the two photons on both sides of the table, sending them to two ground stations separated by more than 1,000 kilometers. And this is today well proven and used for quantum cryptography as well. Okay, so that's it for this second. For the second lecture, this is the outline. The good news that now we are ready for quantum circuits. So tomorrow we see things like that: teleportation, how it works, what are quantum circuits, what are quantum gates, what are quantum algorithms, and how it works, and how entanglement can be used to realize tasks that the classical computers cannot do. Okay, thank you very much. Any questions? Yes, please.
On the picture that was asking, is there so like we are using one photo, right? We have one source for one photo. So is there a problem?
No, it's not one photon. It's a two-photon transition. You know that when you have yes, this, if you are not doing atomic physics, it may seem a bit weird. Photons are absorbed or emitted between when the system has a transition between two levels. Okay, level 1, level 2. This transition can be one photon or two photons or even n photons, multiphotonic, depending on the selection rules and on what transition you are dealing with. So here, inside this blue sphere, what is supposed to be inside is a source of calcium. Calcium is 2 electron atom, okay, 2 active electron atom. It's alkaline earth atom, and it has transitions, 1 photon transitions, but also 2 photon transitions as well. So when the transitions happens, simultaneously 2 photons with different wavelengths are emitted, and they have their polarization is described by this entangled state. So it's not one photon.
Okay, so we do have 2 polarizations, vertical and horizontal polarizations. The probability is that we go sources with the same wavelength, so the same color.
No, as
on the entanglement in this pattern on the other. Is there a probability that we get, for example, blue color or red color?
The 2 wavelengths of the photons used in this experiment corresponded to a very specific transition, and they are well known. I don't remember the numbers exactly of the wavelengths in the nanometers, but they are different, so they have different, let's say, colors. But this doesn't really matter here. Here, what is measured is not the energy of the photons or the wavelength, but only their polarization. Okay, so what matters here is the polarization of the photons, which are measured by polarizers, whose angles can be moved independently. I mean, the wavelengths cannot be controlled. This is what nature gives for this transition, 2 specific wavelengths. That's it. We cannot change that.
Can we expect the entanglement has been shown for photons or electrons to have shown us? Would it be allowed to mention that such entanglement could be also expanded to large molecules, as you have shown us at the beginning?
This is very good question, Malik. Thank you. And I appreciate the question because it can also partially address another question about the Schrödinger cat, as you are going for atomic scale to larger and larger scale. Entanglement is a well-proven phenomenon at very small scale. Why? Because it is very, very fragile. To preserve the state exactly in, for instance, in this kind of superposition, you suppose that there is no perturbation from outside, from the surrounding environment. What we call decoherence, which is the enemy of quantum computers now, and all the properties based on superposition and entanglement. So the problem when you deal with larger systems is that the coherence arrives very, very rapidly, and it is very difficult to handle. So, of course, it is one of the challenges. It has been proven that you have entanglement in large systems, and there is also some speculations about the possibility that it is also the case in some biological systems. Maybe having something to do with life, with consciousness.
Yes.
But it is still very speculative. Maybe it is the case, but it is not proven yet. And the problem is the coherence. So can coherence be said at larger scale? As far as I know, the question is still open.
Another question from parents and police. Otherwise, let's thank Professor again.
So just to show you, and I will not take more time, but at least the first slide of the how can I do just to show the first slide of lecture 3 and lecture 4. Yes, this is thank you. So this is for tomorrow. Okay. Well, I will not go through the slides, just to tell you what we will be dealing with. The quantum gates, what is a quantum gate, how to construct the quantum circuits, and some examples of quantum circuits. This will be the first part in the morning, and followed by lecture 4, and the last one. And the very last part, yes. Sorry, this is 3 again. I need 4. Yes, thank you. The very last part will be about quantum algorithms. What we will do is how to implement and how to understand quantum teleportation. Quantum teleportation and quantum cryptography. So we'll go into details and we will touch the circuits. And maybe if I have time, maybe some hands-on to show you at least the platform of IBM. Very brief tutorial so that interested people can continue by themselves later on. Thank you very much.
Let me take a few seconds about science.
Oh, yeah.
And I have been told that coffee is